All right, Suzuki-san, so we're going to get into the lesson proper, and I might be switching windows a little bit. I'm going to try to remember not to switch to my PowerPoint because I can embed the PowerPoint slides on each of these particular slides. So I'm going to try to stay with this. However, I haven't really scripted this particular lesson out, so we'll see what happens. Homeostasis. This is the lesson you have been waiting for. This is a person hiking up the mountains. I should have taken a picture of me hiking up the mountains this past summer. We went to Hong Kong, and Hong Kong's a really big city, and it's spread out over several islands. It's many islands. There's Hong Kong Island, and then there's other islands I can't pronounce the names. And on our last day before we flew back home, there was this place called the Big Buddha. It's a bronze Buddha. It's the largest bronze Buddha somewhere. Everybody has the largest something. And beside it, there was this trail that goes up a mountain. And we decided that we were going to, I want to go all the way to the top. But most trails, when you go along these mountains, I'm going to use quotation marks even though you can't see me, they go up, but there's often a lot of flat, right? You go up a little bit and then a little bit of flat, up and a little bit of flat. This one was like taking steep stairs, and it never stopped at any point. You're going up the stairs all the way. And I think we went up a kilometer of stairs, basically. It was 40 plus degrees with the humidity. It was incredibly humid, very hot. Our water supply wasn't huge. You think we would have learned from earlier in our trip, but there's only so much water you can bring. And we just kept on going up and up. So as we went up this mountain, as we went up the mountain, certain changes happened to our body, right? And your body's always trying to maintain this homeostasis. So as you go up, you're working harder, your muscles are working. So that means your body needs to supply your muscles with more oxygen. So your heart rate increases to push more blood around your body. So your body's undergoing a homeostasis. You also need oxygen to come to your muscles so that they have, the ability to undergo work. And so you need your respiratory system to move more rapidly to push air in and allow it to diffuse and move around your body. So your respiratory system is changing. There's also homeostasis. If I ate food before or at some point, that nutrients needs to go from my, intestines and my liver stores where the glycogen is and get pushed to my muscles to allow them to do work. And all these changes have to occur. As I get higher up in the hill, and we actually experienced this because we did go high enough, the oxygen level gets lower. And as it gets lower, that means we have to breathe more rapidly to get the same amount of oxygen into our blood supply. So that is also another homeostatic mechanism. So homeostasis is happening all the time with our body. If you look at the word itself, you should be able to figure it out. Now, if you are working through the worksheet, you'll notice that the first activity we're asking you to do is to measure your heart rate. And then once you measure your heart rate when you're relaxed, maybe just after you woke up, or maybe you're sitting in front of the computer for a while, you're then going to run around, do something. Brainstorm with somebody on the phone, on WhatsApp, on FaceTime, and you're going to say, what can we do that's going to either increase or decrease? I would suggest increase because you guys are probably relaxed already. And then do it, measure heart rate. And then what can you do to lower everything down? In class, I'd give you these very sensitive skin thermometers, and they would test your skin temperature. And I'd kind of walk around, and I'd be talking to you, I'd be lulling you into a false sense of security, and wham! I would put down a book behind you when you guys were all like in dreamy land, and your eyes would have all jumped, and your hearts would have started doing what? And you would have taken a big breath, and you would have, if you could feel your temperature or see your temperature, it would go up, it would actually spike, because all these things happen when you get scared. Another homeostatic mechanism. So there's so many things happening with homeostasis. When we talk about homeostasis, it is the balance that we have inside our body, regardless of what's happening outside. Outside could be 0, like it was yesterday morning, or it could be 18, like it was a week and a day ago. And regardless of that, your internal body temperature is still going to be around 37 point something. I don't know if you know this, but it's been shown that over the past 20 years, the human body temperatures, the average body temperature is dropping, which is very interesting. Over the past 50 years. And there's a reason for that, but I digress. I have to be careful because I don't want my video lessons to be 2 hours and 16 minutes. I want it to be much shorter. So the internal environment must be maintained. That's temperature, that's calcium balance, that's sugar balance, that's everything. And in order to do that, you need to have a number of controls. I'm going to explain homeostasis. And I'm going to give you an example of a mechanism using temperature. Okay? So I'm going to use temperature to explain how homeostasis works. So here's the graphic, but I'm going to start fresh. I'm going to use my own graphic. Okay, for homeostasis, I'm going to explain this concept, which includes feedback and antagonistic effects. And so this model I'm going to use here, it involves both. It's something that you'll be using in osmoregulation, thermoregulation, endocrine, nervous, immune. It's a major theme of all the homeostatic controls, and we've seen it in metabolism, and we've seen it in biochemistry. Okay, so let's say we have a stimulus. So that stimulus comes in, right? And that stimulus needs to be registered by your body. So we have this receptor inside our body. So a receptor is able to detect the stimulus, right? And when the receptor detects a stimulus, it needs to send information to a place in your body that has some control. And so we call that the control center. Control center. And as you recall, I'm going to use the idea of temperature to explain this concept. So I'm just going to circle my control center. So my receptor is going to send information to my control center. And then the control center is going to want to send information to something called an effector. I'm going to call that E for short, effector. And the full word is described in the PowerPoint. And the effector is what makes the effect. So let's say this is temperature. So if I'm going with temperature here, if it's too hot, this receptor inside your home could be the thermostat, right? Specifically, the home is a little bit of a difficult one because the thermostat in most people's home, it does two things. So inside the thermostat is a temperature sensor. So we'll say temperature sensor, and that's the receptor. And the temperature sensor sends information to the thermostat, which in many cases is the same thing or they're directly attached to each other. And then the thermostat will then send information to the effector. If it's too hot, then we want the air conditioner to come on, the AC. And so then the air conditioner will send out cold air. And then what will happen is this will send information back to the receptor. And the receptor, when the set point is back to normal, let's say 21 degrees, then it will shut off. So this effector, what it's doing is relying on something called negative feedback. And the negative feedback, it is feedback from the end that negatively inhibits the response, the signal, the transmission, whatever it might be. All right, so let's go into more language here. Inside our body, we have a number of things that follow this exact same process. So we have our stimulus, right? Stimulus. We have our receptor. And then it's transmitted, so there's transmission. Sometimes in the transmission, the signal is so weak that it must be amplified. Okay, so the transmission and amplification often happen in concert. Then the control center receives that information, it determines what needs to happen, and then it will send a signal to the effector. Okay, so the effector, and then that gives us the effect. In this case, producing cold. So you should be able to do the same thing for when it's too cold. When it's too cold, stimulus, receptor sends in information, transmits it to the control center. The control center then goes to the effector. In this case, it would be the furnace. The furnace goes on, and the furnace will heat the place up. Right? So it'll heat the place up. And once again, this will provide negative feedback, because when the temperature is cool enough, it will tell the receptor will turn off, and then the whole thing will stop. So that's negative feedback. See how we have the air conditioner on this side that does the cooling and the furnace on this side that does the heating? Well, together they make up together they make up something called antagonistic effects. So antagonistic effects are when you have opposite effects that do antagonist effects that allow your homeostasis to remain balanced. So if you have too much sugar in your body, insulin is released. If you have too little sugar and you need the energy, glucagon is released. If you need calcium balance, you'll have calcitonin and parathyroid hormone. If it's water, it'll be antidiuretic hormone and something else that will reduce the water loss, that will increase the water loss from your body. So all these things here, negative feedback especially, and antagonistic effects work together to maintain balance. All right, so that is your intro to homeostasis. In the worksheet, you'll see that there is a couple of case studies you can work on. I suggest doing one or the other. Don't do both. One is called Lost in the Desert. The other one's called Lost in the Cold. And both these will give you an opportunity to explore this homeostatic mechanism we've looked at. But specifically, the first homeostatic mechanism we're going to look at here is temperature. Okay? Now, what I want you to do is I want you to think about this. We have these two animals that are very similar in mass. And these animals are the alligator and the black bear. So if we were in class, I'd ask half the class to look at the alligator and half to look at the black bear. And what you'd find is that an average alligator actually weighs a bit more than a black bear. Black bears are the smaller of the bears. There's polar bears, grizzly bears, black bears are smaller. And if you looked at that, that'd be interesting. Okay, so the alligator weighs more. So then if you made a prediction, you might say that the alligator has to eat a lot more food than the black bear. I'd ask you what does an alligator eat, and you tell me fish, deer. He'll eat whatever he can catch in his jaws. Black bear, what do they eat? They also eat fish. They'll eat berries. They're an opportunistic eater, so they'll eat pretty much anything they can capture, but they'll eat both green, veggie, as well as carnivore, meat. Now, the biggest difference is the timing of their eating. Black bears, if they're not sleeping and taking care of their kids, then they are eating 24/7. They're always on the prowl looking for food. Whereas alligators, an alligator gets a good meal. It's good. It's good for a month. If it just eats, it's not going to eat again right away. So it could sit there for weeks, months at a time in between meals. So how can you have this animal that is so big, the same size as a black bear, yet it only eats occasionally? So I give you some time to think about that. And then in class, what it would come down to is something to do with our metabolism. The black bear has a metabolism that allows it to maintain a constant body temperature. The alligator has a metabolism where its body temperature fluctuates with the environment. When it's cold, it goes out into the rock, it basks in the sun, and it gets hotter. When it's hot, it goes back in the water and it cools down. A black bear is able to move around in the colder temperatures. You don't see a lot of lizards in our area because it's too cold. And the snakes that are out in our area, they hibernate. They go in these special hibernaculums. In Center Island has a fantastic, famous one. It's not on Snake Island, but around it. And at a certain time of year, if you go to the right parks, all of a sudden you'll see these snakes coming out of the ground. So reptiles are at the whim of the environment, whereas in endothermic mammals and birds have a little bit more freedom as to where they want to go. And this has to do with the eating. So endothermy, maintaining a constant body temperature, is metabolically very expensive, whereas an ectothermy is cheap. right? Now, as you go through the PowerPoint, one of the things you're going to be looking at is you're going to be looking at all these different strategies that we use in order to maintain a constant body temperature. And for us as mammals, we have to be careful. We have to protect ourselves. If we go out in the cold, then our skin will freeze and the tissue underneath will freeze and the cells could freeze and die. And you get things like frostbite. Severe frostbite ends up losing extremities like your nose and your fingertips and your toe tips and ears and things like that. When you're super hot, your face flushes. So we have a whole bunch of strategies that help us thermoregulate. Remember, this is the condensed version of the lesson, so I can't go into all the detail. At this point, I give you the anecdote of when I had my paper route and I decided that I was going to deliver. I wanted more money, so I took on a bigger paper route, the Scarborough Mirror in Scarborough, and I was on my little bicycle and I was riding around the neighborhood, and it was one of those super cold days, and I think I had like 200 of these little free Scarborough Mirrors to distribute around the neighborhood. I think I made it to about 12. I had my bicycle and I had this wagon that I used to pull these newspapers, and I had to go up a hill, and it was so cold. I didn't have gloves. I think I'd lost them already, and my wheelbarrow was metal, and I was pulling it behind my bike, and I made it to like 10 homes, and I gave up, and I rode to the park and I threw everything in the park, and I think some of them went in the garbage. I rode home in tears and my fingers were frozen. I felt they were going to blow up because it was so cold, because of certain mechanisms that our body uses to maintain temperature. If cold blood makes it to our heart and our central cavity of our body, then it can shock your organs and cause things to stop. So your body does everything it can to maintain a hot temperature. So when it's cold or hot outside, when it's cold outside, your body will close these precapillary sphincter muscles on your blood vessels and stop blood from flowing to your extremities to keep your blood in the core where it can stay warm. But this sacrifices your extremities, and then they get very cold, or they might lose their oxygen and they might die. If you're super hot, we know that you can radiate heat out of your face and your fingertips very quickly. So many people, when they're hot, their skin flushes. We have this ancient response that when we're scared, our hair will stand on end. But this pili erector response is designed to hold a layer of warm air, a layer of air around our body, and air is an amazing insulator. We don't have enough hair for this to work for us, but other animals still use it very effectively. There are some animals that have tissue, fat tissue, that will undergo a chemical reaction that produces heat. It's just a factor of that particular kind of fat. Fat also has insulation properties. So we have all these mechanisms that are designed to help us thermoregulate. Some of them are physiological adaptations, some of them are biochemical changes, some of them are metabolic changes. So as you go through the worksheet, you will see that graphic I told you about. You can't complete it yet because you need to know more about the endocrine system to complete it. But when you do complete it, you'll have a better understanding of how thermoregulation works. That brings me to the end of thermoregulation. So one of the questions I ask you is, what is an advantage of being ectothermic? Do you notice that when you go to sleep that your body temperature changes? Right? Have you ever noticed in the morning how you have a certain body temperature? You should try it. If you have a thermometer, measure yourself before or as you're falling asleep, measure yourself just when you wake up and see what's happening to your body temperature. You can't monitor it all night. I doubt you have that kind of recording equipment, but see what happens to your body temperature. So sleep and circadian rhythms and thermoregulation do have connections. We'll come back to that a little bit later. I'm going to end this particular video. In the next video, I'm going to do osmoregulation, and that will be it for the first week.